Hello and welcome to our lesson on functions, function notation, and compositions. Before we get started, I just wanted to kind of let you know that this first unit on functions should be a refresher. Hopefully you're not seeing too much material that is new, but what we're going to try to do is dust off the cobwebs and get us ready for each subsequent module, which is going to be a focus on particular types of functions. So we're going to lay the foundation and talk about some of the generalized ideas with functions here. So what does it mean for a relationship, a mathematical relationship, to represent a function? Now, before we get started with the note sheet, I just want to distinguish between a couple of vocab words for you. So if we're looking at the expression I have there in blue, it's exactly what I said. This is what we call an algebraic expression. Now, can you distinguish between that one I have in blue, the one I have in red, and then the one I have in green? Are you noticing some differences? Well, hopefully you are. The first one, again, is called an expression. There isn't an equal sign in an expression. That would be something that we try to simplify. So if we were to simplify this expression, we would combine the like terms, like the 3x and 2x, to make 5x. We would combine the 1 and the -7 to make -6, and that would be it. That would be our simplified algebraic expression. Now, if you look at the second and third, so the red and the green there, both of them contain an equal sign, but they're distinguishable as well. So the second one that I have in red has an equal sign, but just one variable. Now, when it has an equal sign, we can call it an equation instead of just an expression. And what we do with an equation when it contains one variable, in general, is we try to solve it. So we try to solve an equation. So in this one, for example, we would start by subtracting 1 from both sides of this equation. So we subtract 1, that would say then 4x has to equal 16. We would divide both sides by 4, and we would get a solution for that equation. Okay? Now the third one in green still has an equal sign, so technically it's still called an equation. But when the equation contains two variables, and it follows certain rules, then that equation could also be classified as a function. And what is it that we try to do with functions? So we simplify expressions, we solve equations, and what we try to do with functions is we graph them. Okay, so we're going to get into some of the specifics about graphing as we move along the unit, and I'll show you some technology tricks to help with those things as well. Okay, so when we're looking at a function, we're looking at an equation, so there's going to be an equal sign. We're looking for two variables to be in that equation, but there's got to be a little more to it. There's some rules that have to be followed in order for that relationship to be classified as a function. So a relationship between two quantities is what we're looking for, two variables, and usually, it doesn't have to be, but usually those variables are going to be x and y, could represent a function. But again, it's got to follow some rules. If the relationship between those two variables that you're looking at is a function, then each x value, every x value, has to correspond with, or can correspond with, exactly one y value. Okay, so that's kind of fancy talk. So what we have to do is look at different situations like a set of ordered pairs, look at a graph of a function, or look at an equation for a function and determine if the rule actually applies. Is what we're looking at, does it represent a function? So each x value corresponding with one y value may be a little tricky for you to think about. One way I like to view it, because it corresponds exactly, is to think about x values as people and think about y values as their birthdays. Because in the same way that every person can have just one birthday, every x value for a function can correspond with exactly one y value. So think of the x's as people and y's as birthdays, and it's the same rule. Okay? So the relationship between these quantities variables, again, when we're looking at a function, is something that we can graph. Expressions we simplify, equations we solve, functions we try to graph, and then graphically we're trying to, again, determine if that rule holds. Is the graph that we're looking at, does it represent a function? What we're going to be looking for is it passing something called the vertical line test, and we'll come back to that in just a second. Okay, so we have some examples here. We have to look at these different scenarios and determine, do we have a relationship that represents a function? So does our list of ordered pairs, does our picture, does our equation, does it in fact represent a function? So the first example, we've got all these ordered pairs, we've got all these different x values, and they correspond with all these different y values. So what do you think? Does that set of ordered pairs represent a function? Well, those are all different people having different birthdays. I think we're good here. So this is a function. No issues there. Okay, how about number 2? So number 2, hopefully you're seeing it. We've got an issue. So this x not an issue, this x not an issue, this x not an issue. But what's happening here is 2 corresponds with 3. And now here's 2 again corresponding with a different y value. So get rid of this just so you can see this a little bit better. Here again, this is like person 2 with a birthday on the 3rd, and here's person 2 again with a birthday on the 8th. Well, you can't be one person having 2 different birthdays in the same way you can't have one x value corresponding to 2 different y values. So this is not representing a function here. Okay, you have one x going to one y, here's the same x going to a different y, that's no good. So this is not a function. Okay, third example, 0, 1, 2, 3, 4, 5, 6, 7, 4, 5. So you may be thinking that this 4 repeats. That could be a problem for us because the 2 repeating and the other one created a problem. But this says, this one is saying person 4 has a birthday on the 5th, and here's person 4 again with the same birthday on the 5th. It's like putting an exclamation point on the fact that you're person 4 with the birthday on the 5th. You can say the same thing twice, you can have the same point twice, this is still considered a function. Now when that 1x goes to 2 different y's, then we have an issue. Okay? Alright, how about this number 4 here? Might be thinking that it's an issue because that y value is repeating in every single one of those points. So 0 maps to 1, 2 maps to 1, 4 maps to 1, 6 maps to 1, but that's not going to be a problem. This is like 4 different people sharing the same birthday, right? Those 4 different x's can all map to the same y. That is still considered a function. Okay. Now the next 3 examples, we're trying to see if the same definition holds. Does every x correspond with one y? But because we have a picture, we can apply the rule a little differently. So what we wrote a few minutes ago was that we could use something called the vertical line test as a really easy way to see if we have a function. What's happening in this first one is technically, no matter where you put a vertical line on your graph, what you want is for that vertical line to touch it once, and that's it. If it touches more than once, that's a failure of the vertical line test. So for example, I'm going to jump to number 6. If I put a vertical line here, because the vertical line touches the graph more than once, in fact it touches twice here, I know that that picture does not represent a function. This is not a function. Now why does this vertical line test work this way? Well, it's basically a visual way to say the same thing we were saying before. So think about this first point where the vertical line touches the graph. The coordinates at this first point are -5, 0, and then the second point here, the coordinates are -5, -6. So you can see it's one person with a birthday, and here's the same person now with a different birthday, right? So every x corresponding to one y, that same definition, we can see applying or not applying using this vertical line test. So number 6 is not a function. The first one over we have over here, number 5, no matter where I put a vertical line, just like use your pencil, right? If you were to drag it, no matter where you put it, it's only going to touch that graph one time. So this one represents a function. Do you know what kind of function this is? And we're going to talk more about these, but hopefully you're recognizing that is what we call a linear function. Okay? How about number 7? Number 7, passing the vertical line test. Let's see if I put a vertical line here, here. No matter where I put a vertical line, it's only going to touch that graph one time. So this, again, represents a function. And, again, we're going to go over these later, but maybe you remember this represents what we call a quadratic function. Okay? Now the last 3 examples here, we're looking at the equation for a possible function. So how do we know whether or not the equation represents a function? So what I would do, the simplest way to do this would be to create the graph. So if I can take these equations and make pictures like we have in 5, 6, and 7, then looking at the picture we can determine right away whether or not we have a graph. So I'm going to use Desmos. I recommended in that module 0 that you download this app as well. If we type in the equation that we're given, it will be able to see the picture and make the determination. So the first one, if we type in y equals 3x minus 1, we're going to see a linear function like we had in number 5, so this is definitely going to be a function, and I'm just going to sketch it out here. So what we see is a graph that looks like this. So again, this is a function, and in fact, just like number 5, it is linear. And if you knew that before we put it in Desmos, awesome. If not, totally fine. Okay, let's type in the next one. We have y equal to x to the third power. We're going to use this a, b button to make an exponent, and then third power, and then we're going to subtract 2 from that, and then we see a little bit of a squiggle in the graph there, but it's still going to pass the vertical line test, so this is still a function. So let me sketch this out, just so we have good notes, and it looks something like this. Still represents a function, still passes the vertical line test. And again, we're going to talk about these classifications later, but this is in fact what we call a cubic function. Okay, how about this last one here? X equals 5. X equals 5 is a vertical line, and if I put a vertical line right on top of that vertical line, it's going to cross at every single point. That would be like one person having an infinite number of birthdays, which we know is not going to be possible. So this is a failure of the vertical line test, so this is not a function. Okay, so hopefully that's a concept you've seen before. And again, the goal here is just to kind of review and dust off the cobwebs. Alright, so moving right along, now that we have established what it means to be a function, what we should also be able to do is use and evaluate with what we call function notation. So to write a function in function notation, basically what we're doing is we're replacing y with something like this, and we would read that f of x. Now it doesn't have to be f of x, it could be, and you see in the examples below, it could be a g of x, it could be an h of x. Really we can use whatever variable we want there. The purpose of function notation is to help us distinguish between different functions. You know, if I just am looking at one function, it doesn't really matter if we use a y or if we use function notation. But if you're dealing with a situation where you have 2 or 3 functions and you're trying to make comparisons, if they're all called y equals, it's kind of hard to distinguish between what's what. So, for example, if we're running a business and we have a function that represents revenue, we have another function that represents cost, maybe we want to call this one r of x, and maybe we want to call this one c of x, so that we can clearly distinguish between the 2 types of functions. Okay? So, function notation, to help us distinguish between types of functions, is again something that we've probably seen before, and sometimes with function notation you might be asked to evaluate, and basically what will happen is the x in the function notation, it could be replaced by a number. So when x is replaced by a number, then we want to plug that number into the function and evaluate, find the value when it's plugged in. So the number gets plugged in. Okay, so for instance, we have f of x equaling negative 2x plus 5. Number 11 here says to find f of 4. So if we have f of x equal to negative 2x plus 5, then f of 4 means we're going to plug 4 in for x. So you see how the x is replaced with 4? Let's replace the x here with 4 as well. So this is going to be equal to negative 2 times, in place of the x, we're going to plug in the 4. And then we're going to add 5. And I just want this to be a little more linear, so I'm going to move this up. Okay, and now we just evaluate. So we have f of 4 equal to, and if you really wanted to just put that in the calculator, you could, but hopefully this is math you can handle. Negative 2 times 4 is negative 8. And then negative 8 plus 5 is negative 3. So we end up with f of 4 equal to negative 3. So that would be the final answer. This side over here, this f of 4, this is just notation. We're not doing any work there. It's not like divide both sides by 4. I know sometimes you see this in multiplication, but this is just notation. So this is it. Now, what does it mean when we say f of 4 equals negative 3? Okay, when we say this, remember what happened was this 4 was plugged in for x, and the result, the output of the function when we input 4, the result here represents a y value. That means if we were to graph this function f of x, there would be a point on the graph when x is 4, y is negative 3. So there would be a point on that graph at 4 and negative 3. Okay, so when we are plugging and evaluating with function notation, what we're doing is we're finding points that are on the graph. So when we say f of 4 equals negative 3, this means that there's a point on the graph of f of x at 4 and negative 3. Okay, now that's not something that you would have to write for an answer every time. I just want you to understand what you're doing. Okay, so let's look at the next one. The next one says to find g of negative 1. So instead of g of x, we're trying to find g of negative 1. That means we're going to plug the negative 1 in where we have an x. So this is going to be 3 times, when we replace x with negative 1, we're going to put parentheses there. We still have the square and then the minus 1. Now again, if you wanted to put that in the calculator, you absolutely could, but hopefully this is math we can handle. Exponents before multiplication. So negative 1 squared makes a positive 1. And now we're going to multiply to make 3. And then 3 minus 1 makes g of negative 1 equal to 2. Okay, so that means if we were to make a graph of g of x, there would be a point on that graph at negative 1, 2. When the input of negative 1 is plugged in, we get an output, a y value of 2. Okay? Alright, so now I have one here that's labeled as a u-try, and I'm going to do this often in the notes, in the lessons you'll see. If I was teaching this class in person, this is where I would have the class try this out, and I can kind of walk around and help if you need, right? But here, obviously I can't force you to do that, but if you're feeling confident with the material, what I would suggest is hit pause on the video and see if you can figure this one out on your own, and then come back to it. If not, and you want to just keep moving along, let's do it. So h of 12, again, instead of h of x, we're going to try to find h of 12. So we're going to replace x here with 12. So we have a square root of 12 goes in, and then we have a plus 4. Well, 12 plus 4 is going to make 16. So this is going to be the square root of 16, and the square root of 16 is 4. So h of 12 is equal to 4 is our answer, which means if we were to make a graph of f of x, or h of x, there would be a point on that graph at 12 and 4. Or this input of 12 makes an output of 4. Or an x value of 12 corresponds with a y value of 4. Okay? Now I just want to go back and make sure that we're all clear on what our answers were. So, boom here, and then one more. Okay, so that's basic function notation and evaluating. You could also be asked to do some operations with this function notation. So if you were, for example, to see this notation that says f plus g of x, f plus g of x means you're going to be adding two functions, f and g. So another way to say this is take f of x and add g of x. So you're just going to add your two functions. Similarly, if you saw f minus g of x, f minus g means you're going to be subtracting these two functions. Okay, in other words, take f of x and subtract g of x. Okay, subtract the two functions. We can see hopefully the operation that's happening in the next one. No symbol between f and g means those two functions get multiplied. Multiply those two functions. So this is f of x multiplied by g of x. And then the last one, the fraction bar there means division, right? Take f of x and divide it by g of x. Divide the two functions. Of course, there's a stipulation on this one, though. G of x, if it's the bottom of the fraction, can't be 0, right? The bottom of the fraction can't be 0. 0 in our denominator is not defined. So we just have to make sure, well, and it's not really going to happen in these basic problems we're looking at, but the bottom of the fraction can't be 0, okay? So we have f of x defined, g of x defined. We're going to try to practice using some of these operations. So number 13, when it says f plus g of x, again, this means to add your two functions. So take f of x and add to it g of x. So f of x is 4x minus 3. And then I want to add to it g of x. G of x is 2x cubed plus 5. Now, just like I was using parentheses earlier to evaluate or to plug the numbers in, I want to do the same thing here. I want to use parentheses when I plug these function values in, or the entire functions in. Now, in this particular problem, the parentheses don't mean much because in front of the parentheses is a 1, and multiplying or distributing that 1 is not going to change anything. And the same thing here, right? Distributing a 1 doesn't change anything. But it is good practice, and you'll see in a later example why it's really important to do that. But basically we're going to be combining like terms here. Since these parentheses don't mean anything, I'm going to go ahead and get rid of them. I still have all the same terms. I just want to combine anything that's like term, any terms that are like, and then make sure that I write my answer in descending order, where the terms with the higher degree are first, and then we descend down to the constant. So I have this 2x cubed and nothing to combine with it, so I'm going to bring it down. And then I have this 4x and nothing to combine with it, so I'm going to bring it down. And then the constants, we can definitely combine the negative 3 and positive 5 to make a positive 2. And so that would be our final answer. So technically, we would say that f plus g of x is equal to 2x cubed plus 4x plus 2. That's the technical full answer with notation, but as long as you understand that's what's happening here, no need to write all that out. Okay, let's try the next one. Next one, fg of x means we're going to be multiplying our two functions. Take f of x and multiply it by g of x. So f of x, which is 4x minus 3, is going to be multiplied by g of x, which is 2x cubed plus 5. So no plus sign in between, no minus sign in between, nothing between the parentheses again because we are multiplying. So we want to distribute. Let's start here. 4x times 2x cubed is going to give us 8x to the 4th. And then we can distribute here. 4x times 5 is going to give us a positive 20x. Distributing here. Negative 3 times 2x cubed. It's going to give us a negative 6x cubed. And then lastly, negative 3 times 5 makes a negative 15. Forgot to change colors. It makes a negative 15. And then I don't have any like terms to combine here. Those are all different variables and exponents, but I do want to make sure my answer is in order. So 8x to the 4th is fine, but that should be followed by negative 6x cubed, and then a positive 20x, and then minus 15. And that would be the final answer there. Okay, so again, I have one that's labeled as utry. If you want to, hit the pause button and give it a shot, then go for it. If not, f minus g of x means to take f of x and subtract g of x. So f of x, 4x minus 3, subtract g of x, which is 2x cubed plus 5. Now in the first problem, the parentheses weren't such a big deal because, again, outside of the parentheses were positive 1s. But here you can see I need to have the parentheses here, especially in the second function, the g of x, because this negative is like a negative 1 here. It needs to distribute to both these terms. I have to make sure I subtract the entire g of x function. So on the first one, the 4x minus 3, that can come down. But distributing the negative to both of those terms makes it a negative 2x cubed and a negative 5. So now when we go to put all this together, the negative 2x cubed can come down, and the 4x can come down, and then we're going to combine the negative 3 and the negative 5 to make a negative 8 altogether. And that would be our final answer on that one. Okay, so I see a lot of sign mistakes happen on that particular type of problem. Make sure with the subtraction that you are distributing the negative to all of the terms that follow. Okay, looking at number 15, hopefully you're seeing a difference here. We're not just looking at two functions, we're looking at under 15 g plus f of 4 this time. So if this said g plus f of x, then it would mean to take g of x and add f of x, right? Well, now it says g plus f of 4, which means we're going to find g of 4, and we're going to add it to f of 4. So that means we're going to be plugging 4 into both functions and then adding the results. Okay, so this one is telling us to find g of 4 and add it to f of 4. So to find g of 4, 4 has to get plugged into g of x. So this is 2 times 4 cubed plus 5. And then plug 4 into f of x. So 4 times 4 minus 3. And those two results will get added. And if you wanted to just put all this into the calculator, I guess I'll show you, you could. So I'm going to put a parenthesis and then 2 parenthesis 4 cubed, and then add 5, close that first one off, plus parentheses 4, and then another parenthesis, oops, too many, 4, and then minus 3, and there it is. So if you wanted to plug the whole thing directly into the calculator, it would be happy to perform all the work for you. If not, totally okay to do it by hand, but we already got the answer, so I'm going to go here with 146. Okay, now in the last three examples, where it was f of x and g of x with no number being plugged in, you can see we still had expressions for answers. Now that we're plugging a number into both functions, we get a numerical answer. Okay, something similar is going to happen on the next one. So g minus f of negative 3 means negative 3 is going to get plugged into both functions, and then we're going to subtract the results. So we have g of negative 3, and then we're going to subtract f of negative 3. So g of negative 3 is going to be 2 times negative 3 cubed plus 5. And then we want to subtract f of negative 3, which is 4 times negative 3 minus 3. And again, I don't want to make any mistakes, silly mistakes with the math, so I'm going to plug this in, and actually I can just correct what I have here. So I'm going to replace the 4 with a negative 3, and I'm going to replace this 4 with a negative 3, and then instead of adding this time we want to subtract. And I believe, just scroll over and make sure. Yep, that captures all the work. So a negative 34 is going to be our answer. Okay, so I have this one last one. If you want to give it a shot, feel free to pause and try it out. Otherwise, well, let's do it. So g divided by f of 1 means to take g of 1 and divide it by f of 1. So g of 1 is going to be 2 times 1 cubed plus 5. That's going to be divided by f of 1. 4 times 1 minus 3. And again, if you wanted to go to the calculator, just to avoid errors, this is going to be a safe thing to do. So when you have a big fraction to type in there, I like to start with the division button. The division button will make the fraction, and then you can type in the top and type in the bottom. So in the top now, I'm going to type in 2 parentheses 1 cubed, and then plus 5, and then on the bottom 4 parentheses 1 and minus 3. And if you don't feel the need to use the calculator, it's totally fine. If I was doing this on my own, I probably wouldn't either, but just to avoid mistakes, it's not a bad thing. Okay, so we end up with a positive 7. And put my calculator away. Alright, so function notation, we can evaluate with one function at a time, or hopefully perform some of these basic operations. And again, hopefully this is looking like review. The last piece to this lesson, we're looking at something called compositions. This is a little more complicated. It tends to be confused with one of the operations at times, but this is going to come back into play toward the end of the unit when we talk about something called inverses. But for now, what it means to find the composition of two functions is you're going to be creating a new function that is composed of two others. So in essence, what happens is one function gets plugged into another. So instead of like finding f of 4 where you plug a 4 into a function, you're going to be finding f of g of x where you take a whole function and plug it into the other. So to find the composition of two functions means to plug one function, an entire function or function value, into another. So the notation, there's two ways you could see this. You could see f and then this little circle and then g and then x like this, or you could see f and g and x like this. Okay, so those are two different notations for how we would say f of g of x. So both are read the same way. Let me just read that again. So this would be read f of g of x, or f of g of x. So you're sort of reading the parentheses or the little open circle there as the word of. So two different ways to find, or that are asking you to find f of g of x, but what that is really asking you to do is to take g of x and plug it into f of x. So just like if I said find f of 4, 4 gets plugged into f. If I say find f of g of x, that means g of x gets plugged into f. So a whole function is going to get plugged into another. So both of these are saying to plug g of x into f of x. Okay? So let's just practice reading a couple of these, and then we'll try this out. So g of f of x, g of f of x. This means to take f of x and plug it into g of x. So f of x gets plugged into g of x. This one says p of r of 2. So this time we have an actual value to plug in. So what we would do here is take r of 2 and plug that into p of x. So r of 2 plugged into p of x. Okay, the notation looks a little different, but same concept here. This is q of n of 5. So n of 5 gets plugged into q. So we would have to figure out n of 5 and take that value and plug it into q of x. And then h of j of x means take j of x and plug it into h of x. J of x into h of x. Okay, so now that we can hopefully read some of these, let's try this out. So 17, we have f of x is 3x plus 4. We've got g of x as 7 minus 2x. We're going to find f of g of x. F of g of x. So g of x is going to get plugged into f of x. So instead of plugging like a number into f of x, we're going to take the whole function. This whole function, g of x, is going to get plugged into f of x. And just like if we were finding, let's say f of 4, the 4 would get plugged in for the x. That's what's happening here. This entire function is going to get plugged in where x is. So f of g of x, f of g of x is going to equal 3 times, in place of x, we're putting in g of x, which was 7 minus 2x. And then we still have the plus 4 at the end. Okay, and now it's just simplifying from here. So we distribute, 3 times 7 is 21, 3 times negative 2x is negative 6x, bring down the plus 4, and then combine like terms. So we've got a negative 6x, and then 21 and 4 makes a positive 25. So we would say f of g of x is negative 6x plus 25. Okay? Next one, similar concept. Two different functions. This time g of f of x is what we're asked to find. So this time f of x is going to get plugged into g. So this entire f of x function is going to get plugged into g of x, and it goes in there where the x is. So we're going to say g of f of x equals 3 times, in place of x, we're going to put in the whole function here, negative 2x plus 1. And then that has to be squared. Okay, and then it's just a matter of simplifying from here. So this is 3 times exponents have to happen first. So negative 2x plus 1 has to be multiplied by itself. It has to be squared. So I'm going to leave the 3. That's going to give us a positive 4x squared, a negative 2x, another negative 2x, and then a plus 1. So that's 3 times, let's see, 4x squared. That's a minus 4x in the middle, and then a plus 1. And then the last step, we can distribute the 3. So 3 times 4x squared is going to be 12x squared. 3 times negative 4x is negative 12x. And then 3 times 1 makes a positive 3. Okay? Oh, we're getting there. So those were functions plugged into functions, and now hopefully you can see we're looking at some function values. And I'm going to scooch this over. Don't you wish you could cheat like this on your paper? Oh, I took too much. That's okay. So this needs to go back. Okay, so on the next one, some function values. So it's p of r of negative 3. So this says to take r of negative 3 and plug it into p. Well, in order to do this, it's not a direct step like the last one, right? If I have to plug f of x into g of x and I know what f of x is, I can plug that in. Well, this one says to take r of negative 3 and plug it into p. In order to do that, I gotta know what r of negative 3 is. So this is going to be a two-step process. First, I have to figure out what r of negative 3 is. So r of negative 3, I find by plugging negative 3 into r. So 4 times negative 3 minus 3, right? Negative 3 has to go into r of x, so right there. And this ends up being, what, this is negative 12 minus 3, so negative 15. So this is asking us to take r of negative 3 and plug it into p. So we just figured out that r of negative 3 was negative 15. So that means we're going to take that negative 15 and plug it into p. So our final answer here is going to be found by plugging negative 15 into p. So p of negative 15 means negative 15 is going to go right there. So negative 15 squared plus 1, which is going to be 225 plus 1, or 226 for our final answer. Okay, 226 for that final answer. And then the last one is going to work similarly. Again, it's a you try. If you want to pause the video and give it a shot, go ahead. Otherwise, let's do this. So r of p of 2 means take p of 2 and plug it into r. Well, in order to take p of 2 and plug it into r, I have to figure out what p of 2 is. So p of 2 means I'm going to plug 2 into p of x, right there. Negative 5 times 2, it's going to be a negative 10. So it says take p of 2, which is negative 10, and plug it into r. So our final answer we're going to find by plugging negative 10 into r. We're going to find r of negative 10. So if negative 10 goes here, 3 times negative 10 plus 1 is going to make, not enough room for me down there, it's going to make negative 30 plus 1, or negative 29, our final answer. Okay, so negative 29 here, just so we're all clear, 226 here, this guy here, and there. Okay, so hopefully that's enough for you to get started with your practice assignment. Seems like enough for our first lesson. So work through the practice, and if you find yourself struggling, just reach out, email, phone, conference. I'll be available Monday morning and Friday morning. Otherwise, we'll see you next time. Take care.